lesson of the year for math. Who's excited? Yeah, I am too. So we're gonna, last time we had been talking about sequences. Today we're gonna talk about series. A series is basically a sequence where we're just adding up some of the terms in that sequence. It could be 5 terms, it could be 100 terms, it could be 10,000 terms, it could be infinitely many terms. And as you might guess, the prospect of writing out like 100 things added together is pretty annoying sounding. Like that doesn't sound like something I'd want to do. So what we've done here is we've created a notation to represent one of these really long addition problems so that we don't have to write out like 100 things added together. So that's called, that notation to represent those very large addition problems is called summation notation or sigma notation. You may see it phrased either way. So this E-looking thing here is like the capital Greek letter sigma, hence the sigma notation. And when you read that, you should read it as the sum of the sequence A sub k from the first term to the nth term. So it's basically saying, okay, we're going to add up these terms of the sequence. We're not going to write down exactly what the terms are because that's super annoying, but you can find them if you have the formula for the sequence. So the k here is like a dummy variable. It's like our index variable, but it's basically the idea. So let's look at some specific examples just to get used to the notation. So the first one is the sum of the sequence 3k from the first term to the fifth term. So the first term would just be 3 times 1. The second term would be 3 times 2. The third term would be 3 times 3, and 3 times 4. And the fifth term would be 3 times 5. Everybody's okay with how I converted the sigma notation into an addition problem? And now that I've turned it into an addition problem, I can just add those things up on my calculator, and we get 45. What do you guys think? NBD? Let's keep going, do some more. So the second example is the sum of the sequence k squared from the fifth term to the eighth term. So we're going to be plugging 5 in for k, and then 6, and then 7, and then 8. So there's just 4 terms that we have to add up there. And again, we'll just add those up on our calculator. So we get 174. So the next series here is the sum of cosine of n pi from the 0th term to the 12th term. So again, I'm just be plugging in to n 0 through 12. Now that's 13 of those things. I don't think I really want to write out all 13 of those, because that seems pretty annoying, and I'm already looking at this and going, with what I know about trigonometry, I'm pretty sure I don't need to write out all of them to figure out what this is. So if I go back to trigonometry, cosine of 0 is 1. Cosine of 1 pi is -1. Cosine of 2 pi is 1. cosine of 3 pi is -1, et cetera, et cetera, et cetera. Every odd multiple of pi is -1. Every even multiple of pi is +1. So if I think about this cosine 0 plus cosine pi, that just gives me 0. So every odd and even pair is basically going to add up to be 0, right? So 0 and 1, 0. 2 and 3, 0. 3 and 4, 0. 5 and 6, 0. 7 and 8, 0. 9 and 10, 0. 11 and 12, 0. Nope, I miscounted somewhere. 0 and 1, 0. 2 and 3, so we should be ending on an odd one, right? 0 and 1, 2 and 3, 4 and 5, 6 and 7, 8 and 9, 10 and 11, and then that leaves cosine of 12 pi with no partner. That's just, it's an even one, so it's 1, so just we're going to end up with a 1. Again, you could have typed that all into your calculator. I'm just trying to not make my life so difficult. The next one, oh no, look at that. How many things are we adding up in that next one? Infinitely many things. Ruh-roh, Raggy. That might be hard. Well, let's see how it goes. So we have sine of 1 pi plus sine of 2 pi plus sine of 3 pi, and keep on going. Now, with what I know about trigonometry, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0. Hey, what do we know here? If we add up infinitely many zeros, I'm just going to get 0. Yeah. All right, mister. What's up? Oh. And then our last one, the sum of the sequence 3 over 10 to the k from the first term to the infinitely many terms. Again, this is kind of scary. I'm going to write these as decimals rather than fractions because I think it'll be more obvious what to do here. So when the first term would be 0.3, the second term would be 0.03, the third term would be 0.003, the fourth term like 0.0003, and so on. When I add all these together, what am I going to get? Just 0.3 repeating, right? Which is just, I recognize that's the fraction 1/3. Now let's pause on that for a second because that's a pretty startling result that we added up infinitely many positive things and got a finite answer out of that. That didn't accumulate to being infinity. Huh! It's a little bit of a surprising result. Okay. So let's talk about finding these sums, because in practice, if there was like 100 of these things, I don't want to have to balloon that thing out into a sum and try to add it all together on my calculator. That's just really stinking annoying. So if we think back to the two sequences we studied in last section, arithmetic and geometric, we can create a formula to find the finite sum for any arithmetic or geometric sequence with just a formula. So if I have a finite arithmetic sequence, my formula is the first term plus the nth term divided by 2, and then times the number of terms that we're adding together. The formula below that is equivalent to the one above it, but I prefer the one above it. I think it's a little bit easier to use. Let's do an example with this then. So it says a corner section of a stadium has 8 seats along the front row. Each successive row has 2 more seats than the row preceding it. If the top row has 24 seats, how many seats are in the entire section? So if I think about this, the first row is 8, and the next row will be 2 more, and then 2 more, and so on and so forth until we get to 24 seats in the row, right? So I recognize right away that this is an arithmetic sequence whose common difference is 2. So if it's arithmetic and we're adding these things up, I want a finite arithmetic series here. We know the first term is 8. We know the nth term is 24, but we still need to find n, right? So you could do it the brute force way and just like write out that addition problem and count how many numbers it took before you got to 24. Not wrong to do it that way. If it was going to be like 100 things that you'd have had to add up, though, that's pretty annoying and awfully easy to get like miscount something. Rather, what I'm going to do is I'm going to write the formula for this arithmetic sequence, which is the first term plus n minus 1 times d. And then if I plug 24 in for a sub n, I can solve for n. And then life becomes pretty easy. So my sum for the first 9 terms is going to be the first term plus the nth term divided by 2 times the nth term, or times n. I think that comes out to be 144. So again, you're just plugging stuff into a formula. The only hitch is that got to solve for n. I mean, this problem wouldn't have been so bad to just balloon it out and just turn into an addition problem and add it up like the brute force way. But imagine if this was like, you know, the University of Michigan Stadium and there's like 70 rows of seats or something. That's all of a sudden pretty annoying. Similarly, if we have a geometric sequence, we can find the finite sum by using this formula. So the first term times 1 minus r to the n divided by 1 minus r. Okay, so example time, if I look at the sequence, they tell me it's geometric. So if I look, it looks like what we're doing is just multiplying by negative 1/3 each time. So there's my r. I'm told the first term is 4. I know this is the last term, but I still need n, right? Still need n to plug into that formula. I'm going to find n the same way I did before. I'm going to write my formula for the sequence. So that's the first term times r to the n minus 1. And then I'm going to plug in the nth term in this problem to a sub n and solve for n. Hopefully it's pretty clear that since everything else is equal, the exponents also have to be equal. So n is 11. So the sum of the first 11 terms is the first term times 1 minus r to the 11th over 1 minus R. And into my calculator that'll go. I'm going to use that fraction, horizontal fraction bar command because, ooh, boy howdy, that looks like it's going to be confusing to get in with parentheses. Oops. Is that a subtraction symbol over that? It's supposed to be multiplication. I just must have missed it. Okay. That looks right. If I hit enter, I get 3.000016935. No big deal, right? Basically just plugging it into a formula. Again, the hitch is that you got to solve for n to get it into the formula, but everything else is given to you. And it's not a difficult proposition to find that n. It's just like a solving problem. So if we talk about a infinite sum, if we're adding up infinitely many terms of a sequence, what we want to do is we want to treat that just like finding the limit of a sequence. So what we're going to do is we're going to look at the partial sums, and the partial sums are going to become terms in a new sequence that we can take the limit of. So when I say partial sums, if we're adding up infinitely many things, the first partial sum would be the sum of the first one term. The second partial sum would be like the sum of the first two terms, and then the sum of the first three terms, and the first four terms, and the first five terms. And each of those partial sums becomes a term in a sequence, and we can basically treat this problem as the finding the limit of a sequence, like we did in the previous lesson. Much like finding the limit of the sequence, if the limit of those partial sums is a specific finite value, we say that series converges, and if it's not finite or the limit doesn't exist, then we say it diverges. So let's take a look at a couple of examples here real quick and try to decide if these are going to converge or diverge by looking at the partial sums. So if I look at A, the first partial sum, well, that's just the sum of the first term in the sequence. The second partial sum would be the sum of the first two terms, and then the sum of the first three terms, and the sum of the first four terms, the sum of the first five terms. And at this point, should be pretty clear what that, if I add up infinitely many terms, what am I going to get? Just looks like 0.1 repeating, right? I think that's the same thing as 1/9. So since that's a finite value, we say that series is convergent, or it converges. If we go to the next one, the first partial sum is just 10. That's the first term. Second is 10 plus 20. The third is 10 plus 20 plus 30. The fourth is 10 plus 20 plus 30 plus 40. And the fifth is 10 plus 20 plus 30 plus 40 plus 50. And here I would say that it also should be pretty obvious what's going on for the, if I add up infinitely many of these, it's heading to infinity, right? Each partial sum is bigger than the previous. And in fact, the rate in which they're growing is increasing each time, right? So we went up by 20 and then up by 30 and then 40 and 50. So this is growing faster each time. That's bombing on off to infinity. So we'd say that this is divergent. Okay. The last one, first partial sum is 1. Second partial sum 0. And then 1. And then 0. And then 1. Now, this sequence of partial sums is just going 1, 0, 1, 0, 1, 0, 1, 0. Is that going to have a limit? If I go out, follow that infinitely many times, am I going to know should be a 1 or should be a 0? No way to tell, right? What do we write in that case? That limit does not exist, which means that that series is divergent. Now, in general, determining whether a series is convergent or divergent can be extremely difficult. That's something that you would study in a pretty good amount of detail in like a second-year calculus course, way beyond the scope of what we're doing here. I will ask you in one situation to be able to tell if a series is convergent or divergent, and that is specifically for an infinite geometric series. And it's really easy to tell because all we have to look at is if the R value is between -1 and +1. If the R value is between -1 and +1, the series converges. And the way we find it is just the first term divided by 1 minus R. If the R value is bigger than 1 or less than -1, then it diverges and you're done. You don't have to write anything else other than that. Okay. So let's look at a couple of examples here. So if I look at my first example, this is the form for a geometric sequence, right? So I can tell the R there is just 0.75. That's enough to say that we converge, since it's between -1 and +1. And my sum then is going to be the first term, which is 3, divided by 1 minus 0.75. Comes out to be 12. Everybody okay with that? Now, if I look at the next one, this is not written in the form of a geometric sequence, right? Not in that typical form. But if I look at it, it's still exponential, right? The variable's still in the exponent. Still means it's going to be geometric. And the base of that exponential is still the value for R. -4/5 is between -1 and 1. So again, this is converges. So I need the first term. Notice that we're starting at the 0th term. So the first term we add up is -4/5 to the 0. Be 5/9, I think, when I do that arithmetic. Again, notice that this one is the same kind of setup as the previous one. So I know that the R, again, is going to be pi over 2. But wait a second, pi is like 3.14. Divide by 2, that's bigger than 1. That thing diverges. I don't have to do anything else. If I look at the last one, they weren't so kind as to give it to me as a sigma notation, so I had to find my own R. That's not too terribly difficult, though. I can see that it's 1/2. So I know we converge. And since it's convergent, I can just take the first term, divide by 1 minus R. So that's 2. Again, kind of a surprising result. I'm adding up infinitely many things and I get a finite number. Infinitely many positive things, I'm getting a finite number. Kind of weird. Kind of weird. And one more example. So one of the things that I can do with this idea of an infinite geometric series is I can take these repeated decimals and figure out how to rewrite them as fractions. So here's the trick. So I have 0.234 repeating. I'm going to rewrite that as like a decimal expansion, where I'm going to rewrite each sum as the repeating segment. Does that feel okay there? No big deal, right? So this is now an infinite geometric series I'm going to think about. I can see that the R value is 0.001, or I'm going to just think about it as like 1 over 1,000. It'll make the arithmetic a little bit easier later on. Again, since that is between -1 and +1, I know that that sum is just going to be the first term divided by 1 minus R. So into my calculator she goes. So 0.234 over 1 minus 1 over 1,000. And then I'm going to press math frac afterwards to make sure it gives it to me as a fraction. And that is 26 over 111. And if I wasn't sure, you can always check it just by typing it in and make sure you're getting 0.234 repeating, which is what we're getting. Feel pretty darn good about that. So that's it for this lesson. From your For this lesson, I'd like you to do 1 through 33 odd. So again, the homework set is here right below the notes in OneNote. And at this point, what are the things that we still have to do that I haven't checked in? So we have the homework from the first problem set from Chapter C. Now this second problem set from Chapter C. We have, and then 2 delta maths from Chapter C. All of this is I'm looking for on Sunday. But you have the rest of today to work on this, as well as class next time to work on this. And then the exam review, again, is due on the 22nd. Yes?
Because we don't have school on Monday, do you still want it by Sunday?
Ideally, yeah, because I want to be able to mark it in, so if you guys see something happened on your OneNote where like it didn't sync through or whatever, that you can have time to do something about it before like exams start and we just forget about it. So that's why I'm asking for it still on Sunday, just that I have time to check it and like you have time to see it and be like, oh, I guess I forgot to do that before like exams start and things just get lost in the shuffle, you know what I mean? So that's it for me. Do you guys have, one other thing. This is a good one. If you have your graphing calculator, take that out for a minute, because you can do a lot of this stuff with your graphing calculator. Let me show you how to do that. So like any of these finite sums, your calculator can do for you. So let's say you wanted to do like number 1 here. So to do that, I can press the math button. And if I scroll down, it's command 0 on my calculator. It's called summation. If I pick that option, it just basically allows me to type in the problem like it looks. The only change I'm going to make is whatever the index variable is, I'm just using the variable x on my calculator. But otherwise, I just type it in exactly like it looks. And then I press enter, and there's my 45, right? So like if I forget this formula, and I just like, oh, well, I know the sequence is this, and I can find the end, but I can't remember the formula. Well, again, you can still do that. Math summation, x equals 1 to 9. And then my sequence 2x plus 6. There's the 144 again, just like we got using the formula. So just, this is a nice tool to have. Yeah, Colby, what's up?
Can you show me just the first part again?
Math command 0. So you press math, and then math, and then you pick the number 0, and there it goes.
Oh.
Okay. So play around with that if you're interested. That's a nice little option to do some of those, or a nice check anyways. Come on, you stupid machine. But that's it for me. I want to point out to you that you don't really have to worry about memorizing any of these sequence formulas. Like, this is the exam equation sheet. I'm so upset with this stupid machine right now. All this stuff should be like hardwired in, so we don't have like all these stupid little like flimsy connectors. Anyway. So again, as you're doing your exam review or whatever, make sure you're taking a look at this and noting like what I'm giving to you. But for the most part, it's, pretty comprehensive. Anyways, that's all for me. I'm going to stop here. You guys have the next 45 minutes or so to kind of get crack-a-lacking on your stuffs. Okie dokes.